Our guest today is Dr. Yiannis Levendis of the Mechanical and Industrial Engineering Department here at Northeastern University. Dr. Levendis' current research is dealing with topics related to combustion, alternative energy sources, air pollution and acid rain prevention, incineration of municipal wastes, engine performance and emissions, combustion diagnostics, and pyometry, polymers, materials development, and polymeric coatings. He is a leading authority in combustion and emissions of and from diesel engines, as well as coal-fired and alternative fuel-fired power plants, including biomass, waste tires, waste plastics, etc. He has developed chemical and physical methods for reducing toxic emissions, has conducted combustion-based materials synthesis, and has developed techniques for fire suppression and extinction. He has conducted extensive research on oxygen-enhanced combustion of diesel, fuel, coal, and biomass. Dr. Levendis is a College of Engineering distinguished professor in the Department of Mechanical and Industrial Engineering. He has published more than 270 technical papers and book chapters and holds 11 U.S. and several international patents. He has received the honorary distinctions of a Fellow of the American Society of Mechanical Engineers and a Fellow of the SAE, or Society of Automotive Engineers. Please join me in welcoming Dr. Yiannis Levendis. Welcome.
How do I start on this?
There you are. You're
okay.
on. Very good.
Well, thank you, George. Ladies and gentlemen, thank you for coming to this presentation of mine today. Well, I'll tell you a few things about engineering design. So design comes in many forms, and in our world, in engineering, we also perform design. Well, as a university faculty, I spend most of my time in teaching, doing research in engineering science, experimentation, taking data, doing analysis, calculations, writing papers, writing proposals, doing service in the university level, committee work, and then react to email, and react to email, and react to email. Now the proliferation of email, it takes so much time every day from our daily time. But since I'm an experimentalist, my work also involves design. What type of design, you may ask? Well, I design equipment to do the experiments. Then I design the experiments, and I go back and I redesign the equipment to fit the experiments that I have in mind. I design materials. I design processes. I also design products. And I occasionally apply for patents. But most of the time, I find that somebody else has already done what I want to do. There are so many patents out there, millions. And there is more than 7 billion of us in the world. When I was born, it was half the population, about 3.5 billion. In my lifetime, we have become 7 billion, and this is going up exponentially. So chances are that many other people have thought about your design. In engineering design, we don't have a chance to do aesthetics very often. But I love aesthetics. When I design products, I like to include aesthetic elements. Well, my sister is an artist, a painter. But besides painting, she also designs and fabricates jewelry. And you see a golden ring in this photograph here. Let me show you the design of a consumer product that I recently did. To do those designs, we follow the process. The same universal process of design. In our world, we call that the engineering design process. But is very similar to the process used in other fields. So we identify the problem, we identify criteria and constraints, we brainstorm possible solutions. Usually we do that in teams nowadays, but sometimes individually. We generate ideas. We explore possibilities. Then we select an approach among the ideas that have been generated. Then we do some calculations, some sketches. We build prototypes or physical models. We redefine the design. We do experimentation and evaluations, and then sometimes we start all over again. And we do iterations, many iterations, and that's the essence of design. You don't get it right the first time, seldomly. Well, what product did I design? Several, but let me tell you one that most of you can associate with. A new automotive oil filter. You say, an oil filter? Yeah, I understand it's not as glamorous as jewelry, of course. It's nested in the engine compartment of a car. Aesthetically, you hardly care about it. It has an important and vital function, however, to filter the automotive oil from any impurities and to keep your engine healthy and running for a long time. Why did I redesign it? Why did I redesign it? Because we have the same oil filter over my lifetime, many years now. And it's not very good for the environment. It's very easy, very durable, very inexpensive, very good for the environment. Usually it's discarded, thrown away. And it's a problem because nowadays, remember, 7 billion of us and counting, we throw away about 1 billion oil filters every year. Globally, and in the United States, about half of that, 500 million. I mean, there are a lot of cars in the United States. There is 250 million vehicles in the United States. You know, they change oil filter a couple of times per year. There is 500 million. Many environmental concerns. Conventional throwaway oil filters that you find in the automotive stores, in the market, are non-biodegradable. They're thrown away, they take landfill space, they contain used oil, and which contains many hazardous materials inside there. And it can create a landfill issue, and it can, let me see, yeah, and it can contaminate groundwaters. How badly? Well, pretty badly. An undrained oil filter may contain up to 1/4 gallon of recyclable used oil, automotive oil. And 1 gallon of improperly managed used oil can contaminate 1 million gallons of water. And you know that water is a very valuable resource nowadays. And is projected to be even more valuable in the future. Imagine the contamination level here. And yet, oil filters, used oil filters, are exempt from hazardous waste regulations by the EPA. Used oil is a hazardous waste. Filters, no. I don't know why. Even if you cut the oil filters, you cannot drain the oil completely. There is always this residual slime in there. Even if you crush them, you cannot get the contaminated used oil out. Plus, you just reduce the volume a little bit. What about our product? Well, it looks very similar to what you have now. Spin-on again, but it's dismantleable. You can open it up. You don't need to throw it away. And then we put a ceramic element inside, which can be replaced in every oil change. And what do you do with the ceramic? Well, let me show you how it looks first. looks like this. You can decontaminate it. You can crush it. It's powder. You can crush it to a small volume and remove all of the oil, the used oil from there. You can thermally regenerate it and reuse it. Or if it is crushed to a powder, you can take the powder and make new ceramic filters out of it after you thermally decontaminate the two. Is it that simple? Well, it seems simple. And I try to make a redesign of the conventional oil filter. Maybe that's not the best solution, but it's a solution. It's a design. It turned out to be a little complicated, how you make it work. How do you allow for a relief valve in case it gets clogged? You don't want to starve the engine from oil. How do you make a retention valve? How do you do the flow? How do you seal the internal parts? It was a project. It took a few years, and it took intensive testing. And we published the results with the Society of Automotive Engineers. And it seems to be performing well now, and by comparison to conventional filters, performs better in filtration efficiency and better in pressure drop. We haven't done any long durability tests, but we are confident that those will be okay when they are done. What about other designs? I'll show you two more. This one here is not a product. It's an energy-related process, an equipment to demonstrate it. Design again. What is the problem this time? Well, waste, plastics. As you can see, this bottle, there is another one there for me, and you may have many more. There is a lot of proliferation of plastics and create litter everywhere, sometimes to the extreme. Of these post-consumer plastics, very little amount is recycled. EPA says 7.7%. No, actually 6.5%. And the rest? Landfill, small amount incinerated. But landfill takes space. Very small weight, but a lot of volume here. And even the little amount that is recycled, what do you do with this? You feel good, I recycle my plastics today, but what do you do with them? They go to a recycling center. They get sorted, cleaned maybe, separated, and then there are very few markets for them. You cannot make another bottle, again, for your clean water. You cannot decontaminate used plastics, unlike metals and glass. So the second generation of material is degraded from used plastics. Yeah, you can make this beautiful chair. And I know that George and the previous speaker like chairs, so I saw you one. This is made from recycled grocery bags. But how many can you make? Not many. Oh, what about this beautiful dress? I mean, I suppose many of you would like to wear that to an event this weekend. It's made out of recycled plastic bags. Can you make many? No, probably it's a unique item. As an engineer, I know that plastics is a petroleum byproduct. So they contain, per weight, the same energy, stored energy, than that gasoline contains, premium fuels, natural gas, per weight. If I can release this energy, the same energy I release, the same way that we release energy from combustion of gasoline, I can reuse waste plastics as fuels. And I can do it in a way that it's environmentally friendly. If you burn your polystyrene coffee cups, and you can do that, it's easy, I did that. it generates, hard to see on this PowerPoint screen here, copious amount of black smoke. Even your little polystyrene coffee cup, it will fill your room with black smoke and many other things that you don't see there, air pollutants, toxic air pollutants. With our process, we can burn it cleanly like natural gas. And this is actually flame from polyethylene and polystyrene cups. So we had to design a process to do that. Now you won't see any glamorous prototypes, but a process. As engineers, we figure out that at the same conditions that we generate a fuel that we can burn cleanly, we can also make carbon nanotubes. So we can do upcycling, not just recycling, we call it upcycling of waste plastics. Get two valuable byproducts of this process: carbon nanotubes and clean burning gas from waste plastics. I won't bother you with engineering details. Oh, you can do that from waste biomass too. Not, after, food has been generated and the residues. Now, we designed equipment to do that, this laboratory equipment. And to demonstrate it, to have a clear demonstration to convince you and to have fun, we also coupled our equipment with a miniature steam engine. And then it runs, generates steam. It has a generator to generate electricity out of the steam with the steam engine. And then it lights up a light bulb. And we can do that by feeding our plastic pellets, in this case, post-consumer pellets, because it's a small laboratory device, to this silo here, process them thermally, generate a gaseous fuel mixture, put it through a flame, burn it, generate steam in a boiler, use the steam in a steam engine to power a generator that generates electricity and light up a light bulb. And that's it. The flame, the steam generator, the steam engine, the light bulb from waste plastics. A lot of design, but you don't have a prototype to see. One more example. This type, again, is inventing and designing a process. And we did make a prototype at the end also. This process has to do with fire suppression and extinction. Why, you may say? Most of the time, we deal with fires with pouring water on them. Not on these ones. There are many of those. This is one at Buncefield in England. Huge fuel, different fuels, diesel, gasoline, fuel storage depots caught on fire by accident. You can see the size of one of them, many of them did, and you can see the size of buses and trucks here. Cannot throw water in an oil fire. It will just become bigger. You don't extinguish it. You need to use some other chemicals, like halon. Most of them are based on halogens, chlorine, fluorine, bromine. Very dangerous compounds. They contaminate groundwaters, they contaminate the atmosphere, they create ozone hole. Many of them are outlawed now, and we're looking for other ones. How big was this? Very big. And what was the worst effect? Loss of property? Yes, of course. Not the worst, though. Loss of life? Luckily, nobody died in this fire. In many other ones, people do. They have fatalities. Air pollution? Sure. You see all of this smoke. It traveled from England to France. But even worse was the groundwater contamination, because that lasted for years. Because they use halogenated foams to extinguish this fire. One day I was experimenting with liquid nitrogen, and many of you know they use liquid nitrogen in many applications, in movies to generate, like things like smoke. Nitrogen is benign. Nitrogen is plentiful. When you breathe, all of you breathe today and myself too, when we breathe, we inhale nitrogen, we inhale air. And you know what percent of volume of air is occupied by nitrogen? 79%. So anytime we breathe, we get 21% oxygen, which we use for our oxygenation of the blood, and 79% nitrogen by default. Nitrogen goes in, it doesn't get utilized, nitrogen comes out. If you bring the temperature of nitrogen, it's number 7 in the periodic table. If you bring the temperature down, you cool it under atmospheric pressure, and you cool it to 77 degrees Kelvin, very cold, it liquefies. And it looks like this. So I was grinding cryogenically tires, waste tires, to make tire-derived fuel for some experiments I was doing using tires, automotive tires, as fuel. And while I was using liquid nitrogen, I thought, well, it's very cold. Doesn't contain oxygen. What it would do if you throw it in a fire? Unrelated activity to what I was doing at the moment. So I lit up a fire, small one, very small one, that big, on the floor. I used alcohol, rubbing alcohol. And then I took some of the liquid nitrogen I had, and I put a spoonful on that fire. And you know what happened? Gone in a split second. It made a nice little sound, and poof. And then it was blanketed for quite some time. It's environmentally benign. We breathe it. It's in the atmosphere. It displaces oxygen. It blankets the fire. It has a cooling effect too. It prevents the fire from seeking oxygen or finding oxygen because it is a blanket over the fire, sealed in that from atmospheric air, and the fire extinguishes. We did calculations. I don't need to bother you with many calculations we did, but there is an expansion of more than 1,000 times of that little droplet or spoonful of nitrogen when it reaches the fire. Makes a big umbrella around the fire. We did some systematic experiments, and we did that with a colleague at an institute in Australia, the CSIRO. And this is a bigger diesel oil fire, 1 square meter. Sits in a pool of water to cool the floor. And then we approached this fire with a cup of liquid nitrogen. We poured it in carefully, and the fire was gone instantly. But how do you bring this to a big installation? How you deliver it? And look back to the Buncefield depot fire again, and there are many of those, big tanks of oil, and you see a fire engine, and you see here, with a nozzle, squirting, well, yeah, can you pronounce this? Perfluorooctane sulfonate foam. It contains fluorine, no good for the environment. It contains sulfur, no good for the environment, a hydrocarbon. They use that. And they extinguish, finally, with some difficulty, those fires. How can we do our liquid nitrogen? It will vaporize. If we put it through a hose, we did quite some experiments on that. And we saw that squirting it away with a hose is not a very efficient method. You have to get close and personal with the fire. You don't want to do that if you're a firefighter. All kinds of tests and calculations and everything, part of the design process, right? At least the engineering design process. Finally, we thought to do it this way. We thought to have robotic delivery of liquid nitrogen close up to the fire. And again, you need to design what type of hoses you need is a cryogen, what type of nozzles you need, what type of truck. Luckily, some of these devices exist because we're not the only ones that want to use cryogens. And we did experiments. And we demonstrated that on a small scale, of course. We cannot do large-scale experiments. And here is our robot. Maybe not as pretty, but good enough. It says Northeastern University on the side. And, oh yeah, some cooking pans. And we put a fuel in there, and we lit up the fires, 4 of them. And then we had this robot remotely controlled with a supply of liquid nitrogen with a cryogenic insulated hose and with a homemade designed nozzle. That's almost my last slide. And we extinguished them one by one, instantaneously, with liquid nitrogen. Well, as you can see, my last slide, there are many expressions of design. Those were mine. These are my sisters. Design has so many different forms. And this is my last slide. Thank you.
First of all, your 3 examples are, each one is enough to talk about for 45 minutes. The oil filter issue, the notion of upcycling, which I think is by itself a great topic, and then this fire suppression thing, but each of which had different cycles, I would say, of design. But let's get started on the oil filter issue if we can. One of the words we've been using a lot and will continue to use a lot is the word context. And it seems that, as we talked about briefly before we came on, the context for designing something like an oil filter has changed. And so therefore, the problems that you're trying to solve have changed. And I wonder if you maybe would want to expand on that just a little bit. In other words, if we've had the same kind of oil filter for 40 years, it's designed in the 50s or 60s, and the nature of the problem was one thing at that point, and it's another thing now. So,
yes, this particular oil filter that all of you are familiar with, some of you may have changed it on your own. Most of us take the car to a mechanic, to a garage to have it changed. It is a device that has been with us for many years, 40, 50 years it could be. And before that, it was dismantleable with paper filters and other ineffective devices, and until the time that somebody designed this one cartridge contain all, and it's very easy to put on. If you can reach, some engines are not that easy to do that, but if you can reach the location, you can then remove it and just put a new one. And maybe 50 years ago, that was not a problem, and everybody loved it, and people still love the easiness of replacement. But back then, we were not that sensitive to environmental issues. Well, after all, the environment wasn't as polluted as now, because there were very few cars on the road. There were very few people, and people were not thinking that way. Nowadays, as I said, in my lifetime alone, we are twice as many on Earth than when I was born, and we have so many cars. Everybody has a car. Many people have more than one, and everybody changes the oil, and then it becomes a big problem, environmental problem, and also a waste of resources. So the philosophy has changed. Maybe it's time to go back to a new design that's more environmentally friendly, and this is what I had in mind. I saw the issue visiting a friend of mine that has a garage, a mechanic, and I saw piles of waste automotive oils, and I said, "What are you going to do with them?" Said, "Throw them away." I said, "Why?" So because that's what we do. There is no law against that.
Right. Well, first of all, whenever you see, and I'm sure that most people here have probably seen driving down the highway, more in some parts of the country than others, when you drive by a real accumulation of the consequences of cars, whether it's a gigantic junkyard or a gigantic pile of tires, sometimes just astronomical number of tires. And these have traditionally been things that people say, well, we'll get around to figuring out what to do with that later. In the meantime, just take it down to the tire dump. And of course, sometimes they burn them, and those fires last forever.
Forever, yeah.
And I love the idea, and this is segueing, I suppose, a bit into your second example. I loved the idea that we are now, by looking at these problems differently, coming up with ways not just of mitigating the negative, but actually perhaps finding an actual positive to come out of some of these things, which it seems to me very encouraging. The business about finding a positive use for plastic waste is something that seems to me will be really game-changing. And forgive me, but I know you're so involved with alternative fuels and alternative energies of all kinds. I have to ask you, this is kind of a timely question, but it does seem like it is one that is about the context of what you do, and that is, just in the last 5 years or so, the context for discussions about energy in this country, it seems to me, has changed completely because of this natural gas issue. Maybe you can help us a little bit with that, because if we were having this conversation, let's say 10 years ago, it would have seemed that whatever your politics, oil was not going to be around forever, and the price of it was going up precipitously, and therefore rendering investing in other alternatives an economically logical thing to do, rather than a utopian pipe dream. This was very economically driven. I'm sure that students here are aware of the so-called, that there's just been an explosion of technological change in extracting natural gas, and it turns out, rather than being energy poor, the United States has an incredible supply of this. How has that changed, your world? How has that changed how you look at problems?
Well, as George said, there is a lot of hydrocarbon fuels now in the United States, especially, but in other places in the world. There is that suppresses the price of natural gas, and it's becoming a very inexpensive commodity, and it puts pressure on development of other alternative energies. This is a fact. Now, we have to keep in mind, though, that a few other issues that appear here. One is that this is a temporary thing. It will be a spike in the long history of fossil fuels, we are going to find more and more of this tight oil or shale gas, and we're going to use it and use it up, and who knows how long it's going to last, maybe another 10, 20, 30, 40, we don't know, years, and then it's going to be depleted again. I mean, fossil fuels are finite. And it may get depleted in our lifetimes, maybe not, but this is one issue. So we have to conserve, and we have to look at alternative energies. Second issue is that this is not the case everywhere. Well, China doesn't have this many resources, consumes a lot of oil, a lot of coal, and imports a lot of it. So this cheap natural gas is not that cheap in other places of the world. Another issue is natural gas still has carbon in it. So there is an issue with climate change. Lesser of an issue than burning oil or coal, but still an issue because the carbon-based fuel. And if we're serious about climate change, we cannot just be looking only at natural gas. It helps, but it doesn't solve the problem. It makes it better. It's like taking an aspirin. But it does put economic pressure on other resources or a development of alternative energies.
It's interesting because, I think a lot of the times, in my field, in architecture, I like to say we're in a fundamentally contingent business. Architects and a lot of designers do not get to simply assert what they are going to do. They respond to conditions that are in front of them. And so sometimes I suppose that can be a bad thing, but oftentimes it's a very good thing because it allows you to deal with changing circumstance. And it seems like this is a profound change in what we thought, even fairly recently, was going to be the kind of arc of energy. We thought that the marketplace was going to increasingly drive economically smart alternative innovations in fuel and energy on, let's say, perhaps a new generation that was not the more utopian, this is what one should do, but rather this is not only what one should do, but what the market will now encourage you to do, which will make a much more natural, less, let's say, what's the right word, less contentious basis for energy development. And I can only think that in your world, this must have really changed that conversation. I mean, because even if, I hear what you're saying about, yes, we still need to be responsible. We still need to plan for the realities of climate change that many, many, many people think are well underway. But absent the clear economic, in the world we live in, absent the clear economic engine for that, it changes it completely, it seems to me.
Exactly, yes. And this is one of the reasons that when we were talking before about the second example, about upcycling waste plastics, now generating a fuel, a clean burning fuel out of the plastics, maybe not enough because there is inexpensive natural gas as a competitor. Therefore, generating a second byproduct, the carbon nanotubes, may make it a little bit more appealing economically.
What are the uses of forgive my ignorance on this, but what are the uses of the carbon nanotubes? I mean, what would that be used for?
Well, there are few current uses, but many future uses because they're developing technology. So people think they will be used in many, many applications. Currently, you may see them in electrodes for batteries. You may see it as additives in different materials. They have very nice properties, high conductivity, high tensile strength, and so on and so forth. So there are many projected uses and a few current uses. So it's supposed to revolutionary many applications.
But seen as a kind of a building block in the nano manufacturing world and the nano medicine and that sort of thing?
Yes.
Yeah, okay. Well, that's interesting, trying to come up with more than one market for like, for example, let me just ask you on this energy front, on this generating energy or fuel from plastics, from waste plastics. what is the price that oil has to be at or natural gas has to be at in order to make that competitive? And how close is it now? Is that a fair question? Do you know what I mean? In other words, there are certain energy types.
No, absolutely. That's a very good question, and we looked at that. If you price, I mean, the easiest way is to price the amount of a fuel, I mean, the cost of the fuel on an energy content basis to compare, because you cannot compare a gas with a solid or a liquid, they're different densities. So let's say the current price of natural gas fluctuates a lot, depending on the market, but it is somewhere between as cheap as $3 per gigajoule in last year to $11, or last 2 years to $11 per gigajoule. Now, waste plastics, it depends. It depends how clean and processed you get them. If you want to use pellets that I was using in these laboratory experiments, they're a little more expensive than you use if you take plastics in bulk. And then will they be washed, or they will be, as received from recycling? Will they be separated, different plastics, polyethylene from polystyrene, from polypropylene, from PVC, and so on and so forth. The price fluctuates, but it is within the fluctuation of natural gas. We're directly competitive now in post-consumer. When natural gas becomes very, very inexpensive, then even the cleaned and separated plastics when it becomes on the upper scale, then even the clean and separated plastics are competitive with it. We're in the same range.
Well, that's both surprising and very encouraging, because a lot of times these things start out as an invention, and of course, or the discovery, and you say, well, that would be interesting once it becomes price competitive, but
right.
As you know very well, there are many energy sources in the housing field that are interesting and very effective, but they're not competitive with how inexpensive natural gas is. So, for example, the payback period on investing in a geothermal heating for residential use is often 50 years or more. Well, let me switch gears just a little bit. And we've talked about context. We've talked about the notion of what question you're answering or what problem you're solving. I'm going to raise another word that might not seem as relevant to what you were talking about, but I think it is in a way. One of the other words we use when we talk about design in this class is empathy. And by that we mean the ability of the designer to actually put him or herself in the shoes of the user or someone other than themselves. It's essential. To be a good designer, you have to be able to understand the thing or the process from the point of view of somebody else. And at first I thought, well, this isn't going to be so relevant for Yanni. But actually I think it is, because there are, and you've actually already alluded to it, there are different audiences, in a way, if you could put it this way, for energy use. In other words, there are the people who want to heat their home, but then there's also the people who are the neighbors to the power plant. There are also the people that live in a neighboring state, as we know from acid rain, that is 3 states away, that are affected. There are people in different industries that provide the infrastructure for, gas stations versus electric charging stations and so forth. I wonder, in your experience, not only in your own work, but in other people who are in alternative fuels, if there's a way for those kinds of things to be folded into thinking about alternative fuels. Do you know what I mean? And maybe that's more of a policy issue in a way than an engineering issue.
But yet it is very relevant to the design. I mean, even when you make a wind turbine, you may generate problems, and you say, well, the wind is there, so I want to harness it. But there can be problems that you generate. First of all, an aesthetic problem. I mean, you put an eolic park on a nice mountain slope, it would not look as nice as before. You can generate noise if you live in the vicinity because of the noise of the rotating blades. Could affect the ecosystem, flying birds through those turbines. They can be, even if they move slowly, Of course, they have very, very large diameter. So there could be some, so the designer has to be aware of this, and the legislator has to be aware of where they put all of these devices.
You know, the question of wind turbines is such a great one, and I was hoping that we could kind of drift into other energy issues, because, you know, I get a big kick out of the idea that, and it has, as we both know because we've been here for a while, the issue of wind turbines aesthetically on Cape Cod has been, I don't, many of you probably don't know this, but it has been a dramatic and politically charged discussion about despoiling the view of Cape Cod or the Atlantic Ocean by putting wind turbines out in there, because there's tons of wind and it's really consistent, and it'd be a really great place to generate energy. And I must say I have been astonished at the uniformity of the view that it will despoil the landscape. Because, you know, there's another way to look at this, which is the Dutch, for example, for hundreds of years, have had these unbelievably picturesque windmills that are, you look at a Dutch painting for over a 400-year period, and you see this beautiful landscape dotted with windmills, and they're not hiding them, they're highlighting them. They're not trying to make them blend into the landscape, they're showcasing them. And the idea that this is inherently, I don't know, this comes from a view of the environment that it is completely separate from the human beings who occupy it. And it's not that we can't put ugly things in the water. I suppose we could, but if anybody's ever seen a windmill, even these gigantic GE turbines, I think they're quite stunning. And especially if you put 50 of them in a row. Anyway, this is one man's opinion, but I find it stunning that everyone seems to agree, at least in the terms of that debate. Even the people who are in favor of the windmills are saying that they're in favor of them purely from a performance standpoint, not ever from a visual standpoint. And that's an op-ed I need to write, because
they can overwhelm the aesthetics of a particular location, because there's so many of them.
Yeah.
It's not just a few dotting the surroundings. But again, I have mixed feelings about that too, like you, George.
And of course, the consequences are not only visual. They are, in some cases, they create sound or the bird issue, as you've discussed. Well, okay, excellent. Another thing, I was so grateful for your diagram about the engineering design process, which is indeed the design process for everyone. Mm-hmm. And it's the writing process for everyone, right? I start, I have an idea, I write a bit, I try to outline it maybe, I write a bit, I read it, identify the ways in which it is terrible, the ways it is irrelevant, the way it is not doing the job, and I go back and I start again. And it's a cyclical, iterative process. Another word that we use is visualization, and this, I imagine, is something that has changed what you do enormously. The ability in the digital age and the computer age, I mean, the difference between when you started in your field and now, in terms of your ability to visualize your ideas. How is that, for example, in the work with your oil filter? You know, I imagine you had very detailed digital models, like in AutoCAD or something like that.
Yes, I mean, and as you mentioned, it has changed a lot in the last few decades. When I started, we were doing drawings by hand. Mm-hmm. And now you do drawings by the computer. Not only you do two-dimensional drawings, but with the new software, you do three-dimensional drawings that you can rotate in front of you on the screen. And you can do a lot of work with that. As you saw, some of these are pictures, some other ones are three-dimensional drawings. It would be good to do a prototype. In engineering, we like to do a prototype also, because the drawings can only tell you that much. Now, with the 3D printing, maybe it will make prototyping even easier than before.
Right.
You don't have to do it in clay or in actual material. You can do it with 3D printing. and it's getting to that point, not quite yet.
But you know, just to build on that, I think that sometimes, you know, and this because as you know, in architecture, you know, this revolution has been really dramatic, but it doesn't take away from the need to have a kind of vision of what you're trying to do in the first place. I think sometimes young people get persuaded by the technology that we have, the ability to draw in such detail, the ability to rotate and see things in 3 dimensions right away, which is great. But at the end of the day, you still have to know what the problem is that you're trying to solve.
Yeah.
If I showed you a really detailed vision, my vision of a new oil filter that was just a really, really good 3-dimensional model of a paper filter that you couldn't take apart, that wouldn't really advance the ball at all. And yet it would, sometimes it seems like it does because you can visualize the thing.
Yeah, physical prototyping is still very important, especially if you want to test it. You have to have the real thing to test.
Are you able to, you know, in many fields, there's a level of modeling that you can do on, are there ways that you can test flow and filtration, for example, in a digital model in your work, or no? That has to be done with a prototype and actually running oil and impurities through it.
There are computational fluid dynamic CFD packages that you can test flow also. You can test stresses, you can test temperature gradients, velocity gradients, very nice. But there are things that you cannot test, like leaks, imperfections, problems, and those have to be done by prototyping. Because the models assume a real world, an ideal world, and the real world is very often very different.
Let me jump back to something we talked about, or that you talked about before, and it had to do with the upcycling. You spoke about the latent energy in the bag of plastic bottles, and you know that's the sort of thing I should have probably already known, but it really struck me that there is so much in the waste product that we produce. I'm sure not just plastics, but plastics because it's so much of a oil-based, petroleum-based enterprise. I assume there must be a lot of work being done in this area.
Yes.
What are some of the other problems that people are taking on? If you're working with the sort of plastic bottle business, what are some other slices of that? How do we get the most out of our petrochemical? How do we use our petrochemical stuff more than once?
Mm-hmm. Well, to get the stored energy out of the plastics, you need to chemically react them with oxygen, what we call combustion. You need to burn them. And this is only when you get that particular energy I talked about out of plastics. Now, you could burn them as they are in mass incineration, but you know, we have been there, done that. It generates a lot of pollution. You saw the polystyrene cup burning in direct combustion. It will generate the same or similar amount of energy, but it will create an air pollution nightmare. The way we do it is we need to have premix, not diffusion flames, but what we call in combustion science premix flames with air. So we put the right amount of air with the fuel in order to burn it cleanly. But to do that, to have premixed air with the fuel, you need to have the fuel in gaseous form, not a solid. So we go through a pyrolytic gasification first. And we do it at an optimum temperature that we can also generate catalytically the carbon nanotubes. Then we have the fuel, and then we can deal with the gaseous fuel and burn it cleanly. And that's how we liberate this energy from the plastics. There is no other way to get that energy out, like combustion, like we do with other fuels.
Mm-hmm. Another thing that I wanted to talk to you about was this, the fire suppression
Yes.
work that you're doing. That seems especially, I mean, gosh, how many explosive, fire-laden scenes have we seen just in the last couple of years down in Texas and Louisiana and places like that where they have so many of these plants. I would think this is there must be a great market for this. Are you working with any agencies or government agencies on this? Because it seems like the best practices that we have now are really bad, are environmentally, like this is what I like to say, the bar is really low for improving this. If we're poisoning the ground every time we put out one of these fires, and it takes a long time to do it, it seems like your proposal is, gosh, why aren't they doing more of it already?
That's a very good question. We have been talking to people, we've been talking to oil companies and legislators. There is a lot of inertia in the system, a lot of particular interests of people that make the extinguishers. They want to promote their product. We didn't have any widespread luck yet, but we have been talking to people.
Have you thought about this is now a design review. I was interested to see that how much energy had been put into creating the truck that would carry the cold material, then the special, super complicated insulated hose that would then take it to the robot that would then ultimately drop it into the fire. But how many people in here were thinking, why don't they just drop it from like a helicopter? Anybody? It was the first thing that occurred to me. Why would that not be a much more efficient? In other words, very much the way you did it in your lab. It's just that instead of the spoonful, it's a helicopter that's above this horrific fire and just drops it right in. And is that something that you guys have thought about, or?
Yes, we have, and this is a very good idea, and it can be a possibility. There are some issues, though, with that it is a very highly volatile liquid, because it is liquid at very low temperature, 77 degrees Kelvin, and room temperature is 279 Kelvin, so it is like 200 degrees higher. So if you transport it under atmospheric conditions, it vaporizes very quickly. It needs to be held in insulated thermoses,
Nice.
Then as you drop it, then it will just be a big liquid mass dropping on the fire. It will also lose a lot by vaporization in flight. So we haven't done these big tests yet, I have to admit, but we thought a lot about this, in just to dump it or in a balloon as a bomb, right, like a water balloon,
right,
and drop it on the fire, and that is definitely a possibility.
Right.
But by hose and a robotic application, you have more control over it.
Yeah.
Now, it's not an exotic material. If you look at our chemistry building, heard it? In the back of the building, there is a big silo of liquid nitrogen. So the truck comes off and replenishes that. We store it here on campus. Very big one, from here to the ceiling. So just if you walk around the chemistry building, you will see it in the back of the building.
So it's used for lots of things.
For lots of things, yes. For any, many cryogenic applications that you need, very low temperature.
Right. Interesting. Let me get back to our words here. We talked a bit about what drives innovation in fuels and alternative fuels, and really, as much as anything, it seems to me, it's price. It is the price, because fuel is a commodity and not a brandable. As much as Shell Oil might try to sell you gasoline that's a little bit more expensive on the premise that it's way better, the reality is it gets sold by the gallon, and it's just, or by the barrel, and it is what it is. And so I guess innovation is driven as much, I suppose to some extent by regulations. If regulations change, CAFE standards go up in the auto industry, that fuels innovation, even if the price of oil remains the same. But are those the two big engines? Regulation and the price of oil, or the price of...
Yes, absolutely. regulation is cognizant to the price, but is also very cognizant to the environmental effects or other issues. And, is a philosophical outlook. Is it only price, or you have to be concerned about other things? And some people are concerned about other things.
Well, I guess what I would add to that is the way that you get everybody concerned about those other things is through regulation. In other words, it's just like in the building industry. We don't get to build just whatever we want. For example, we're required to build things that you can get out of in a fire. I do not have the creative option to build a building without fire exits. That's not on the menu.
Right.
And since everybody has to do it, it makes it part of a marketplace. And I guess it's similar in the energy world. Now here's something that is in the same vein but slightly different. That is, another word that we talk about a lot is what are the metrics? What are the ways of measuring success in these different areas? And one can imagine, maybe you can talk to us a little bit about how success is measured in alternative fuels. I suppose these circle back to the various constituencies that talk about who your customer is in a way, who your client is. But when we talk about alternative energy, how do we measure? So we know how we measure the energy output, but how do we measure the success of one mode versus another?
Well, it's a good question. We can look, let's say, at biofuels. Biofuels, we use biomass. And if we use biomass, then we compete with food supplies. We don't want to do that because that's not a successful use of biomass. We have to use residual biomass or waste biomass to generate fuels out of that. And then it's a question of cost. If it's renewable biomass, it's good because then it is considered to be carbon neutral. You use that much carbon dioxide to generate biomass, and then you release that when you burn it, but it is, neutral, almost. But if it's not renewable biomass, then it's a moot point. If you cut, the wood to put a Walmart there at that place, it's not renewable biomass. Then you have to see, now water, to generate biomass, you need a lot of water, and water is a price commodity nowadays. It will be even more priced in the future, so that works against biomass. Then you have to have a fuel, biofuels, that have some advantages over, the petroleum-based fuels. They have to be as energetic. They are not. There is a lot of oxygen in biomass. That reduces the heating value of the energy content. And then they have to be burning effectively. They have to not create more problems in the combustion system, like slugging and fouling and other deposition and clogging the injectors in an engine and so on and so forth. There is a lot that goes on there. And then the emissions have to be cleaner than what it is from petroleum. Other emissions, not just carbon-based, but sulfur and chlorine and nitrogen emissions, nitrogen oxides and other things. So it's a very complicated equation. You cannot just say that alternative energies will be better than the existing ones. They can be better, but there is a lot of design that goes into their operation to make them better.
Again, thinking as a designer, one of the things that would certainly rationalize and demystify those choices in some ways is if we agreed upon a consistent measuring system for subsidy, actual cost, let's say environmental cost, dollar cost, reusability, and so forth, so that you could really compare, if you want apples to apples, what your choices are. Because oftentimes, it seems to me, just as a day-tripping observer of the energy conversation, things are very seldom being compared to like things. In other words, oil and gas have one set of parameters, solar and wind and other so-called alternative measures have another set of measures that make different assumptions. And it would be, as with so many things, it would be helpful. A real design solution here might actually have to do with metrics, interestingly. Yes, we need new products, but maybe we need a new and consistent way of measuring success. I find that's not uncommon in the design world, that if the bar is moving all the time about what constitutes success, it's hard to compare things.
Absolutely, yes. And also the discussion about biomass that I was talking about, it reminded me a very interesting question to ask. You see this wooden table. How was this wood generated? I mean, you say from trees. And how was the wood in the trees generated? From carbon. And where did that come from? Did it come from water through the roots? Did it come from the nutrients in the ground? Does anybody know?
I don't.
Yes? It came from CO2 in the atmosphere, from that invisible carbon in the atmosphere. And there is very little CO2, parts per million in the atmosphere. Indeed, it's going up now because of anthropogenic sources, combustion. So it's, let's say, 400, the latest, 400 parts per million of carbon in the atmosphere. We breathe it. Now, trees also through what process? Do you know the process? Photosynthesis, right? And they generate mass of carbon on their trunks, and then we get, this. And this is why biomass is considered to be carbon neutral, almost, because of this. Absorbs CO2 from the atmosphere to generate this woody material, and lignin and celluloses, and then we
release it back.
We release it back when we burn the wood, and it goes in a cycle again. Yes.
Yeah. Well, that's a great example. In fact, a sort of life cycle cost of any of these things. It would be very revealing because their greatest cost or greatest benefit might exist at a different point along that continuum. I think I understand very, very much what you're alluding to. It's not as though there's simply a batch of bad fuels and a batch of virtuous fuels, which is the lens through which we are sometimes led to understand it, but rather we need to understand the real costs and benefits of each of them all along the life cycle.
Absolutely. Even coal, which is the dirtiest fuel of all, because it's mixed, with soil and dirt and everything. When we burn it, all kinds of pollutants coming out and a lot of carbon dioxide too. Even coal can be burned cleanly, and a lot of people are doing research, and I'm involved in research on clean coal, how to burn coal cleanly. There are ways. It will be a little more costly, it will increase our electricity bill, but it can be done, and we are working on that.
Finally, I want to ask you something that is an interesting question, I think, for a lot of designers, and that is, maybe it's more straightforward for somebody who does research. The eighth word in our list is leadership. And it seems to me that, we all make choices about what we research, what we do, what we choose to look into. We have only so much time, and maybe you want to talk about, how you try to, I think you've shown us, but I think maybe you want to say a few words about how you try to lead in your field, how you try to change the nature of the discussion or advance the discussion.
Well, it's not an easy thing to have leadership in one's field, because you have to have a vision of the future, right? And to show people how to get there. How to get there meaning how to get to your vision or how to get to a common vision. It's a little unclear how you do that in design. But certainly you could shape the future in your field with what you're doing. It's a very elusive thing. I don't know if I can comment on how I will do that. We all try to do it subconsciously by having new things, new inventions, new ways of doing a design of a product or of a process. So in some ways, we're all trying to do that. But we're also influenced by what other people do because there is all of this proliferation of publications and conferences today, so you get ideas. Usually, most of the time, most of us will do small things, like small steps in a process, and breakthroughs are rare. Sometimes they're happening, and those could be bright spots that can show the future in a field, but it's very difficult how to describe a process that does that.
Well, you know, it's interesting because I take your point, of course, that not everything can be a breakthrough. But on the other hand, and it's all of this is point of view, I suppose, but I would argue that many designers are at some level leaders because it's their job to show people something that doesn't exist yet, and to, as we've said, reverse engineer a way to get to that thing. And I realize that, you know, let's say the upcycling of plastics into energy, that you're not the only person doing that, but it is an act of leadership through design, it seems to me, that gets people to look at that. For example, to look at plastic not just as a refuse problem, but as an energy source.
Yeah.
That is looking at the world differently and then reverse engineering a way to achieve it. And I think that's what designers do. At least that's, I think that's what a lot of designers do. And of course, in this course, we're trying to broaden the definition of designers so that it includes, appropriately, I think, people who do what you do and do what lots of our other guests do. I want to open it up to students now, and if any of you have any questions for Dr. Levendis, please feel free to come up and ask them. Please.
As carbon nanotubes begin to be implemented in the design of solar cells, do you think that upcycling would help increase the viability of their use?
The viability of solar energy?
Yes.
Okay. I suppose anything helps. If the solar cells become cheaper based on this, then it will be only helping this field.
It's still pretty unclear what these carbon nanotubes are going to be used for. Is that what I heard from you before?
Yes, it depends on the application, but we can lower the cost by having, the source of the feedstock, the primary feedstock coming from a waste material. And if you don't have to buy it, if you have the recycling center, if you are, let's say, City of Boston, and you take the recyclables to the place, and then you use them there, and you don't have to transport them to other places and so on, so the cost will even go down. It will be even more competitive to natural gas. There are processes now that make carbon nanotubes from natural gas, and we're competing against those, and natural gas is inexpensive.
Yeah.
So that goes back to what George was saying before. Natural gas prices are not helping us in promoting this process.
Please.
Hi, yeah. So my question is related to functional design versus aesthetic design, and that's kind of what I mean by that is like with the wind turbine debate. Right. They are very functional, but apparently they're not very aesthetic, so it kind of is not a successful venture. Have you seen like more examples of that in your work, where the functional design is there, but the aesthetic design isn't, and it just doesn't work out?
Yes. It's a very good point, and I was giving it some thought before I came to this lecture about aesthetics. I mean, aesthetics are very important for me. But then aesthetics have many forms. Functions have many forms too, but aesthetics have many forms. Most of the time, personally, I associate aesthetics with the visual form. But it doesn't have to be visual. It could be oral, right? I mean, it could be aesthetics in taste. A very nice, a very good cook can make, an aesthetically food, but it's not visual. It's not oral. It's a matter of taste. It could be tactile. It can be many things. There are aesthetics even in invisible things like mathematics. You could have some people, mathematicians, call a solution elegant solution to a mathematical problem. It satisfied their aesthetic criteria. I mean, because they call it elegant, right? Elegant is associated usually with the visual part or oral or the arts. Even in physics or chemistry, even in a process, it could be an elegant process. That means it doesn't have a lot of extras and peripherals, that it just goes to the point. So how to talk about aesthetics versus function? Most of the time we think about those visual aesthetics and the function, but they take many forms.
Yeah, I mean, you can certainly cite examples. I mean, maybe one of the easiest to think about is bridges, because bridges are a fundamentally, they are a structural problem. How do I get from one side of the river to the other side of the river, for the most part, or one side of the gorge or the other side of the gorge? But they are not only functional problems, because the difference between, if you doubt it, the recently completed Bay Bridge in San Francisco that was they've spent 15 or almost 20 years, I think, since the earthquake of, more than 20 years, since the earthquake of 1989, which destroyed parts of the Bay Bridge in San Francisco. Now they've just opened the new one, and the difference between the two is remarkable. Both still succeed in getting people across from one side to the other, but they are very different aesthetic operations, and I think it's noteworthy. But you don't want to hear me prattle on about that.
My question has to do with the aftermath of the liquid nitrogen. So once it extinguishes the fire, what is left to clean up from it? And is that cost going to make it more effective to kind of balance out the costs associated with travel, like moving it and creating it, and then the robot and everything to actually use it?
Yeah, who's going to pay for the robot?
Yeah.
Exactly.
What is left after the application of liquid nitrogen? Nothing. It diffuses into the air, into the atmosphere. It's part of air anyway. So just add a little bit more nitrogen to air, it just disappears. And you don't want to apply it, though, in a closed space, because it displaces oxygen. So if you have a lot of nitrogen and not enough oxygen because you release extra nitrogen in a closed space, it could be asphyxiating. So this is only for outdoors applications, not for indoors. Unless there are no people indoors, you evacuate the place first and you can release it indoors too. You have to be aware of that. And what was the second question again?
Do you think that the cost effectiveness of the cleanup would balance out the obvious costs of implementing?
The cost is very inexpensive.
Right.
You can buy
compared with the expensive cleanup of the halon.
I mean, the expense of you can never clean it up. It goes into the groundwaters. It goes everywhere. It is a potent contaminant. Those halons and everything, those foams. But how expensive is liquid nitrogen? Same price as bottled water. You can buy it for $1 a gallon.
Wow.
In retail, if you buy it in bulk, it will be much cheaper than that.
I guess the only remaining thing would be what would be true in both cases, which is, let's say if there was an oil fire, there would still be the residual oil there.
Yeah, the residual
but that would be true in either case.
It would be true in either case.
Okay. All right.
I kind of have a counter to what she's saying, because you speak about the cost, but then you think about the firefighters, the hot shots who died in Arizona, the 19 of them, and they train year-round to be the best of the best when fighting fires. And it's just, you get to a point where there's human error. So, the cost shouldn't matter. If you can create something that's both environmentally safe and then uses a robot to extinguish fire, the price shouldn't matter, because if you aren't hurting the environment and you aren't risking the death of an actual person, and it can completely extinguish this massive fire, then I think it's an amazing solution.
But you're not talking about this, though, for forest fires. This is for oil fires, right?
Yes, it's mostly for those chemical challenging fires that they don't extinguish with water. It could be used in a forest, but it complicates because the robot cannot go between the trees easily, unless he could, and carry the hose with it or carry a liquid nitrogen, but he could. Forest fires may not be the best application for this unless you do it from a helicopter.
But even with oil fires, you're still
Yes.
going to have the risk.
Or any other chemical fires, that you have airport fires where there is a spillage of fuel and the airplane is burning and all kinds of things like that.
But I'm sorry, you were going to say one other thing?
Oh, that was
No, okay.
But let me go back to aesthetics because I'm also a little bit confused about that. Maybe you guys can help me, maybe George can help me to understand a few things. The example of the bridges was again visual. We have the visual image of the bridge that looks good, and then it has a function. So it seems that most of the time we talk about aesthetics, we are talking about the visual impact. Let me ask you a question now. What about the aesthetics of food? Okay, you go to a nice restaurant, they do design, they make the place look nice, they design even the presentation of the food. So you get a plate, and it looks good, and it tastes good, right? If they do the right job, it looks good, and it tastes good, and it smells good. Let me ask you now, what is the aesthetic part of this presentation? The looks good, the smells good, or the tastes good? And which out of all of those sensory inputs you will associate aesthetics with? Or all of the above?
In that case, I would do it in the visual.
Most people would, me too. But you know what aesthetics means? In Greek, aesthesis is the sense. It covers all of them. Would you, I don't know, I'm asking, I don't know the answer, would you associate aesthetics also with the smell?
Sure, and
What about the taste?
Of course. I mean, we've all had the experience, probably, of having some vaguely gray soup or something like that really does not look very appetizing, but you smell it, and then you taste it. It's absolutely delicious, but it looks like, it looks like mud, or it looks like, you don't know what it looks
It
like.
will turn you off, right?
Whereas,
Yeah.
you go to a minimalist fusion restaurant with a giant white plate and a tiny little, incredibly designed meal at the center. You enjoy it enormously even before you taste it.
Right.
And it might actually not be that good.
So it seems that the visual impact it will be the most important in this case.
I think it's the
By
most
far,
refined.
right?
I think it's the most...
So that's why we associate aesthetics with the visual impact.
What do you all think?
I mean, obviously, when my sister designs this, it's all about looks. Because it has no smell, no taste, no nothing. I mean, other senses don't play a role. Tactile a little bit, maybe, but in other cases, like food, I mean, there are so many senses that take part in evaluating food.
Yeah. Please, come on.
So on this aesthetics kick, do you think it may be whatever sense the thing you're analyzing hits first? Because maybe you'll smell something and then you'll go looking for it, and it's not until you find it that you find out it's visually not aesthetic. So do you think that whatever sense you use first on the object defines how you see it aesthetically?
Yes. Now, let me ask you this question. What are the aesthetics in music? There's nothing visual there.
Right. Well,
It's all oral, isn't it?
that depends on if you're at a concert or not, because somebody could play the guitar beautifully, or somebody could just hammer it out, and it could sound good, but it could look absolutely horrific.
And if you don't see the person, if you just listen to it,
Then it's all audio.
it's all oral, isn't it? And then, I mean, you may be delighted by a nice symphony or whatever music you like, but, and, I mean, you hear Vivaldi's Four Seasons, and it may be a delight if it's executed nicely. And, but it would please you find a lot of aesthetics or aesthetics in that music, but there's nothing visual there.
Right. Does it kind of creates a vision, though,
Maybe.
So you,
Imagine things. Yes.
It's true, but of course, in aesthetics, there are whole sets of relationships and proportion and balance and so forth that apply across fields, across senses. In other words, one can talk about music and architecture, for example, in using a very similar vocabulary
Right.
of rhythm or sequence or pace, things like this. So, it is interesting to think about, and I think that your point, the last speaker's point, is very well taken. That maybe the one that is the entry sense is the dominant one in determining things, even if they appeal to more than one. And it's just that often that entry sense is visual. For those of us who are sighted. Now, for those who aren't, of course, there's lots of writing about how they perceive the world completely differently because the lead sense is a different one other than sight. So I think that's interesting. All right, folks, I think we're going to wrap it. Let's thank Dr. Levendis.